Okay, this is 8M2, lesson 15. An informal proof of the Pythagorean theorem. What I'm going to do with this lesson is I'm going to break it into two parts. So, because there's two keys. There's the part of this lesson where you have the informal proof of the Pythagorean theorem, which many of you are going to need to know. Maybe some of you don't have to know this, but it all depends on what your teacher's telling you you have to know. I'm going to show you the informal proof today in this lesson, and then we're going to do a second lesson that's going to be the usage of this, of the Pythagorean theorem, where we're going to work through some problems. So again, let's just go about proving it, and then I'm going to do another video that's just going to have the homework help and the lesson application. So let's go to, let's cut to it. Just a second. Just give me a second to get this Okay, here we go. All right, so this is an informal proof of the Pythagorean theorem. And the Pythagorean theorem, as you know from class, is in a right triangle. The sum of the squares of the legs equals the square of the length of the hypotenuse. And the hypotenuse, this is just another word for the long side, or the side opposite the right angle. Right, so in this right triangle, we have a 90-degree angle here, and the side that doesn't touch the 90-degree angle, it's opposite. This is called the hypotenuse. And the rule says that the sum of, that if you take the length of side A, and let's just say that in this case it's a 3, and the right, the other leg, side of 4, if you square the 3 and add it to the square of the 4, you get the square of the third side, the hypotenuse. So if we plug in our numbers, we get 3 squared plus 4 squared equals c squared. And 3 squared plus 4 squared is 9 plus 16. That's 25 equals c squared. So c equals 5. Okay, it doesn't always work out to be an integer number, a whole number. It doesn't always work out that way. But in this case, there's certain numbers that actually will work out. So let's prove why this is true. At least informally, we're going to prove that this is true. So this gets a little bit, maybe a little bit difficult, but bear with me. I'll try and go slow, try and show you each point. Now, the first thing that we're going to look at, I'm going to do this in GeoGebra because I think that the shapes are just going to be a little neater and easier to see. Some things are a little bit harder to show. But, wait, where do we, how do we just draw? Reflect. Here, let me cancel. I just want to do freeform text. I used to be able to do this. I might not be able to just write over a freehand shape or pen. There we go. They moved it over here. Okay, so I can say, here we go. I'm gonna show you triangles. We're gonna make 4 triangles that are congruent. Right? And these are going to be right triangles. 4 triangles, 4 right triangles that are congruent. So notice in this case, and you can always do this, and I'm just going to use nice, easy sides. So in this case, I'm going to have one side that's a 3 and one side that's a 4, okay, in my proof. And so notice that these are all reflections or rotations or a combination of each, right? Because in this one, this is a 3 and a 4. To get here, I simply translated translated this guy up, and then I rotated it down. Okay, so these are congruent. And again, notice that, oh well, whatever. Shoot, can I undo? Undo, yeah, there we go. Let's get this all just right. Okay, now, because this has a side of 3 and 4 right angles, so these are all translated or mirrored, and you can see how this one becomes this one if I mirror it, or I rotate it, I translate it up to here, and then I rotate it around, and this one similarly is this one translated over. It's this one, man, translated over here, and then rotated 90 degrees about E. Okay, so those are our 4 triangles. And making 4 triangles is just, again, it's a trick that I use to show that these that the Pythagorean theorem is true. You wouldn't know to do that other than the fact that that's the trick that helps you show it. And now watch what you can do. And remember that angle A and angle J are congruent, and angle A and angle N are congruent, as are angle D, angle F. So N, J, F, and A, they're all the same because these triangles are congruent. So they have the same sides and the same angles. Similarly, this angle here, this angle here is the same. Let's just draw these, because this is really important. These angles are all the same, as are these angles are all the same. Now, one thing to notice as well, that if we have a right triangle, a right angle on all of these triangles, and I'll get rid of all these markings in a second, that the sum of the angles must be equal to 180, because this is one of our key building blocks that we're going to need to know, or going to need to show ultimately this proof. So watch what happens. If angle A plus angle C plus angle B equals 180 degrees, which we know it does because it's a triangle, and if angle B is 90, so angle A plus angle C plus 90 equals 180, then I know that angle A plus angle C equals 90, right? And then I know that I plus J is 90, L plus N is 90, and D plus F is 90. So now we've proved this. I'm gonna erase all of this drawing here because it's kind of in the way. And then we're going to get rid of all of this. It's all just in the way. Okay. And we're going to write that angle A plus angle C equals 90. And remember, angle J plus angle I equals 92. And these other two, L plus N and D plus F. Now that I've drawn this, I want to move them together. This is the next part of our proof. So we're going to snap these guys into place, and we're going to show something interesting. The key is that the next key is I want to show you that this entire, I'm going to break, let me just draw this for you. This entire area, the entire area that I've drawn, this entire shape, we're going to cut it in 2 different ways. And when I cut it in 2 different ways, you're going to see that it doesn't matter how I add up everything inside this perimeter, but the area inside this entire piece must be the same no matter how I cut it up. So if I cut up two triangles or I cut up a bunch of squares and I add up all the pieces, they have to be the same. So let's show this in two different ways. Now I'm going to ask you some questions and I'm going to want you to answer it, but watch how I break this up. Okay, so we're going to cut this guy like this. And now I'm going to ask you, how big is this piece here? How big is this piece? That's the question to you. Well, first of all, from here to here, remember, this is A. This is the same, this triangle is the same distance as this. It's 4 in this case, but let's just call this side A, right? This triangle from this square from here to here is A. And from here to here, how long is it? Well, we have another side over here because we know that this is A. And let's just draw all of them in. I mean, we know that that's A and that's A. Well, we'll stop there. So this has to be A because from here to here is A. This is also A. Now let me draw you another square. This is a different size square. How big is this square? Well, from here to here, we know that this size is 3. We've already shown that. This is side B. Right? Remember, we have a triangle that looks, let's just draw this triangle. It looks like this. And we are calling this side A, this side B, no, sorry. We're calling this longer side A, and the shorter side B, and this is C, right? This side, short side of this triangle is B. The long side is A, or sorry, the longer leg is A. So in this case, from here to here, this is B. Also, we have from here to here, don't look at this long side, look at from here to here. Well, it's the same length as from here to here, right? If we just take this piece and move it all the way down, this side here, from here to here is B. So we have a square that's B on one side and B on the other side. So let's look at these two blue pieces. These two blue pieces, well, one piece, this is A squared, and this one here is B squared, right? So if we just look at, I'm going to draw this a little bit darker, right? If we go from here to here, and here to here, and here to here, and here to here, we have B squared, and here we have A squared. Now we have to ask ourselves, how big is this piece and how big is this piece? Well, we know that if this side is 3 on this side and 4 on this side, or this is B and this is A, then this triangle is A times B. Or this rectangle is AB. Okay, so this whole piece in here, and let's just draw, we'll draw this one in hopefully like red or something. That whole piece is AB, and how big is this whole piece? This piece is also AB. All right, this is AB because this side is B, and this side here is A. So we have A, and this is side B. So the whole area of this big square, we can write it as A squared plus AB plus AB plus B squared. And that's also A squared plus 2AB plus B squared. Okay, so the area, so now I've cut this into pieces, and I've identified that if I add these 4 pieces together, I get A squared plus 2AB plus B squared. Now watch what happens when I choose to do it another way. I'm going to cut this guy another way. All right, this was AB. Somehow my stuff disappeared, but I have these, these 4 pieces here. We're going to go back and we're going to draw these same triangles. And again, you can make your triangles any size you want. I just used 3 and 4 here because they fit nice. I'll fix that one in a second. Bear with me. They fit nice, but you could have made them 2 and 5 or 3 and 6 or 1.5 and 2.5, but you've got to make all of them the same size. These are all congruent triangles as we've proved. So now what I'm going to do is I'm going to put them all back together the same way we did before, and I'm going to, what I call, cut them differently. Now the key thing to remember, there are a couple key things, well, there's a couple key things here that we need to know. Now, first of all, we know that this angle plus this angle are 90. Remember, we measured this, and we said that this angle here plus that angle is 90. Well, this angle is the same as this angle, so this angle plus this angle is 90. Well, if this plus this is 90, and this whole angle here is 180, then this must be a right angle. That must be a right angle. And this must be a right angle. And this must be a right angle, and this must be a right angle. And you can figure that out using the same rule that we used before, because all of these angles look like these measures. So this, if these are all right angles, then this turns out to be a square. Now let's go back and look at this shape one more time. We're going to draw it again here. And we're going to label the sides. Again, we're going to label the short side B, the longer leg A, and the hypotenuse C. So if these are all C, and this is a square, then this whole piece in the middle, let's make it blue, this is coming in nice and clear. Watch this. This has to be C times C. This has to, the area of this whole center thing is C squared, because this is a square with sides of C. This is looking really cool. Now, we're going to add up the area of these 3 triangles, and we're going to make them green. So watch what I do here. And these triangles here are all the same size. So if I find the size of any one of them, I can find the size of the other 4 without having to recalculate. So let's look at the size of any one of these triangles. Well, we know this triangle is B, and this is A, and this is a right angle. So the area of this triangle, if you remember back into 7th grade, is half of the base times the height. So this is a half AB. This is a half AB. This one must also be a half of AB. And this is a half of AB. So what is the area of this giant square, the one that goes PTB1W? If we add this whole thing together, well, we got to add up our 5 pieces. So our area is C squared plus a half AB plus a half, whoops, what did we do? A half AB plus a half AB plus a half AB. Well, a half AB plus another half AB is 1AB, plus another half AB plus another half AB is 2AB. So this is C squared plus 2AB. Well, if I cut a pie or a square or anything or a field one way and add up all its parts and I get a certain size, and if I cut it another way and add it up and get it another size, then it must be the case that these two things are equal. So A squared plus 2AB plus B squared equals C squared plus 2AB. Well, by the law of subtraction then, I can just subtract 2AB from both sides, and I get A squared plus B squared equals C squared. And I have informally proved the Pythagorean theorem. So, hopefully, this was a useful proof for you. Your teacher may expect you to know how to do something along these lines. And I encourage you to watch it once or twice. If you or do it in GeoGebra, maybe do it on your own graph paper, whatever you need to do. But I recommend that you give it a go. And hopefully this was a helpful proof. If not, then just put it out of your mind and watch the other half of this lesson, which will give you some good homework help. And thank you for watching. I really appreciate all of my viewers. You guys are the reason that I do this, the fact that anyone gets use out of it. I like doing math. If I did math in a forest and no one listened to the tree fall, would I be doing math at all? I don't know. Whatever. You know what I'm trying to say. Take it easy. We'll see you next time.